Hello, everyone. My name is Tristan, and my contributing sensor to Professor Ellery's Europa Moon mission is a seismometer for measurement of subsurface ice movement.
Hello everyone, welcome to my live demonstration of my single-axis seismometer here. So let's begin. So while the data is printing, I'll show you more about the apparatus and how I'm collecting the data here. The data is being streamed live to MATLAB, where it will be processed and completed. Here is the apparatus. As you can see here, it's held down in 4 different locations to ensure it is rigid. I've marked down some important dimensions and locations of testing. As you can see here, this will be important for the multi-sensor network. Now, let's take a look at this data here.
In the current working model, raw acceleration data is directly collected in MATLAB from an Arduino Duo connected to an IMU. As part of the electrical interface of I2C, a pair of pull-up resistors are used to avoid shorting the circuit, one between the serial data line and the voltage, and one between the serial clock line and the voltage. A live plot is generated to ensure the data is actually being collected.
And once this is done, you get a nice beep, beep.
Once the accelerometer data is done being collected, the raw data is then saved as a table for post-processing. The unfiltered acceleration data may have biases and offsets, and to address this, the mean value of each axis is subtracted from the data to remove the DC offset. This was also applied to the integrated velocity component to prevent the culmination of errors. Additionally, raw acceleration data often contains noise and low-frequency drift. To remove low-frequency components, a second-order high-pass Butterworth filter was used. To obtain displacement, the acceleration data was integrated twice using the time step of the frequency of data collected by the sensor, where the displacement data was detrended to remove any drift. The MATLAB code plots the displacement data recorded in the X, Y, and Z axes. The waveforms captured oscillatory motion with the X-axis representing time and the Y-axis representing displacement. Frequency domain analysis was applied to characterize the oscillatory motion further. MATLAB's fast Fourier transform FFT algorithm was used to extract the dominant frequency components from the raw acceleration data. This provided insight into the nature of the simulated seismic activity and served as a baseline for distinguishing between different vibrational modes. The accuracy of the processed frequency data was validated by calculating the input frequency of the test apparatus. Using the 6 centimeter perturbation, it was determined that the input frequency was 22 Hz, which matches very closely with the results of the sensor frequency analysis. This confirms the system's ability to capture motion with high fidelity. The multi-sensor system integrates 3 MPU 6050 IMU sensors, each connected to the I2C splitter through the various I2C buses, which is directly connected to a central Arduino Uno microcontroller. The I2C module provides precise time synchronization for all sensors, ensuring accurate time sampling of seismic wave arrivals. Each IMU captures 3-axis acceleration data independently, while the shared clock signal coordinates their operation. Triangulating the epicenter of a seismic event requires the analysis of the time difference in the wave arrivals at each sensor. The system calculates these time differences by comparing the timestamps of peak amplitudes in the recorded frequency waveforms. Using these differences and the known position of the sensors, the location of the seismic event can be determined by examining the frequency shift recorded in the frequency and magnitude plots. The lowest frequency spike in the Z direction indicates the closest sensor to the perturbation. The highest frequency spike in the Z direction data indicates the furthest sensor from the perturbation. This is due to the setup of the test apparatus, as locations further along the moment arm will vibrate at a lower frequency compared to the fixed one. These results validate the response of the event localization technique of the multi-sensor network and are consistent with expected results. To conclude, this project successfully designed and validated a seismometer-based 3-axis accelerometer for detecting seismic activity. The system processed acceleration data into displacement and frequency waveforms, visualized as seismographs, and provided critical insights into the vibrational characteristics such as frequency, amplitude, and duration. The hardware design progressed from a single sensor setup to a multi-sensor network, enabling for the localization of seismic events through a triangulation technique. Thank you. Here are my references.